Hey guys, this is the video that's going to be covering section 6.5. It is the final section video of chapter 5, and then I'll have one more video covering both 5 and 6 in preparation for the test. So that one's going to be labeled under chapter 5 and chapter 6 review. I think I already have the answer key for those problems listed on Canvas, and I have the problems listed as well. I think I have it in a PowerPoint. So if you go to where the section PowerPoints are, the chapter 5 and chapter 6 review will be there as well. So we're going to go ahead and get started with this one. There's only 2 objectives that we're going to be covering in 6.5. Factor the difference of 2 squares and factor the sum or difference of 2 cubes. All right, so before we get started with example problems, just a little bit of background information. Factoring the difference of 2 squares, there's a rule. So basically, when you have a perfect square minus a perfect square, then this is the setup of the binomial times the binomial every time. And it does have to be a minus sign. If it's a square plus a square, that won't work. It has to be a square minus a perfect square. So the rule is if you have a squared minus b squared, and the a can represent anything, the b can represent anything, then you'll have a plus b, a minus b. So all you do in order to get your a and b is take the square root of a and take the square root of b. Now, a and b are just representing the, really just anything. It could be like a number, it could be a variable, but basically you're taking the square of whatever that perfect square is. Okay, so for our example, first example, I should say, we have a squared minus 16. So I know that a squared is a perfect square because this is a 2. Really anything that's a variable alone that has an even number is a perfect square. So right now, 2 is a perfect square, but I could have a to the 4th, I could have a to the 3rd, or sorry, not the 3rd, a to the 6th, a to the 8th, a to the 12th. As long as this is an even number of a variable, it's a perfect square. For 16, I know it's a perfect square because 4 times 4 makes 16. So the way that we do this to represent when it's a perfect square minus a perfect square, you take the square root of a squared, so that would be a times a, and the way you get that is just simply this number divided by 2, so 2 divided by 2 is 1a and 1a. If it had been, say, like 6, it'd be 6 divided by 2, which would mean a to the 3rd, a to the 3rd. So you're just dividing it by 2 when it's a variable to an even exponent. For the number, you can actually take the square root of a number in your calculator if you're not sure if it's a perfect square. But in this case, I just happen to know that 4 times 4 equals 16. So I put 4 and I put 4. Okay, so this one goes first, this one goes second. Then as far as the signs, one is going to be plus and one's going to be minus, and it's that simple. Okay, so why don't you go ahead and do the practice problem? And then I'm going to do it on the board for you to check your answer. Okay, so x squared, 2 divided by 2. So my perfect square is 1. And then 81, the square root of 81, I know 9 times 9 makes 81. So I have x plus 9, x minus 9. All right, example 2. So we're still doing the same thing, except for now we're throwing in both variables and numbers into the same term. So we have 3 that we're going to look at here. Okay, we're going to do these first, and then I'll do C after we do these. Okay, so in this, obviously the x squared, that's going to work because it's an even exponent. 25. Can I take the square root of 25? Yes, because 5 times 5 is 25. And 1, what is the square root of 1? So what times what makes 1? 1. So if I break this down, I take the first term first. So do the coefficient. So I know both of these are 5. And then x squared, if I take the square root of that, it's x and x. Now, for the second term, it's just the number 1. I know that 1 times 1 equals 1. So 1, 1, one of them's plus, one of them's minus. All right, so on this next example, 16a squared minus 49b squared. I know that both the first term and the last term are perfect squares. So what I'm going to do now is go ahead and draw my 2 binomial sets. Take the first term, 16, the square root of 16 is 4 because 4 times 4 equals 16. A squared, it's even, so I'll have A and A. Then for the second term, do the coefficient first, 49. Does something times something, the same number, equal 49? Yes, I know that 7 does. 7 times 7 is 49. That's a perfect square. Then b squared, I'll have a b and a b. Last thing, 1's plus, 1's minus. Example 2. Oh, okay. All right, now for the third example, letter C. This time we have a fraction, z squared minus 9 over 16. So you're probably like, well, how in the world do I know if a fraction is a perfect square? So think of it this way. We know that in a fraction, whenever you multiply a fraction times a fraction, the tops multiply and then the bottoms multiply. So in order for a fraction to be a perfect square, that means both the numerator and the denominator are a perfect square. That doesn't mean they're the same number. It just means that the numerator can make a perfect square and the denominator can make a perfect square. And it has to be that both the numerator and denominator can be squared, not just one or the other. So in this case, I noticed that I do have an even exponent in my variable. So this is a perfect square minus a perfect square. So the first one is obviously going to be z. Now for this, I take the numerator and the denominator separately. On top, what's the square root of 9? 3. On the bottom, what's the square root of 16? 4. So I'll have 3/4 on both of these. One's a plus, one's a minus. Okay, so now it's your turn. The practice problem you're doing is letter B. That can be found on page 401. So letter B, you go ahead and try it on your own and then check your work with me. Okay, so in this one, perfect square minus perfect square, the square root of 36 is 6. The square root of a squared is a. And then for 49, I know 7 times 7 makes 49. And for b squared, then I divide it by 2. So 2 divided by 2 gives me b to the first and b to the first. One's a plus, one's a minus. right, when finding squares of variables, keep in mind their exponents are being multiplied if squared. Simply divide their exponent by 2 to find their square. So I've actually already talked about this. This is if we're working with variables, okay? It's not the same way necessarily. I mean, it does work with numbers too, but most of the time you're not going to see a number with an exponent. You're going to see the number just as the number. So really this rule is applying to when we see problems that contain a variable. As long as it's an even number, you can take the square root of it, and you do that by dividing by 2. So if you look at the example I gave, I said y to the 10th is equal to y to the 5th times y to the 5th, because you add exponents when it's on a variable. So all you do to get that is divide by 2. 10 divided by 2 is 5. So that's how I knew that y to the 5th times y to the 5th equals y to the 10th, a perfect square. So we're going to do m to the 4th minus n to the 14th. So as long as both of these variables have an even number, that means that I can take a perfect square of it. So in this case, m to the 4th, if I divide 4 by 2, I get 2. So that means both of these are going to be m to the 2nd. For n to the 14th, that's an even number, so I can also take the square root of that. So 14 divided by 2 is 7. So I'll have n to the 7th, n to the 7th. To finish it off, one's a plus, one's a minus. All right, you go ahead and try the practice problem on your own. I'm going to go ahead and work it on the board, and you check your work when you're ready. Okay, on the example problem, or sorry, the practice problem, p to the 4th, 4 divided by 2 is 2. So p to the 2nd, p to the 2nd. Q to the 10th, 10 divided by 2 is 5. So q to the 5th, q to the 5th. 1 is plus, 1 is minus. All right, if a binomial contains 2 squares being added, it is considered a prime polynomial and can no longer be factored. When factoring, if you find your binomial can further factor, continue factoring. So let's work through this problem, and then we'll talk about what this phrase is really telling us about. Okay, so what I notice is this is even. So that means I can take a square root of it. 256, we can take the square root of 256. I want to say, might be 16. I'm going to check that though, because I'm not 100% sure. This is when a calculator would be handy. So if you're not sure about a number, just type it in your calculator and take the square root of that. And the square root, if you're not sure what that symbol looks like, it's that button. So just press 256, that button, and it will show you what the answer is. Okay, so I was right. It is 16. So we know that this is 16. I'm going to go ahead and write that in. Now for p to the 4th, it's an even number, so 4 divided by 2. So that means I'm going to have p to the 2nd, p to the 2nd. One's plus, one's minus. Now, here's what that statement was telling us before we did this practice problem. It says when factoring, if you find that one of the binomials can further be factored, you need to keep on factoring. So if I look at both of these, obviously I can't factor anything else with this. But what do you notice? The whole entire section is about factoring perfect squares. When I factor this into a perfect square and a perfect square, or factor these two perfect squares into our plus and minus set, notice on this one, and it only applies to when there's a minus sign. P squared, is that a perfect square? 16, is that a perfect square? Yes. So sometimes when you factor a perfect square, you can end up with another perfect square. So if that's the case, you need to keep on going. Don't stop your answer here or it's considered wrong. So I'm going to rewrite this +1 because it's still part of the final answer, but I'm just not going to do anything with it. So since I know this is a perfect square minus a perfect square, I'm going to go ahead and draw another binomial set because that means I can keep going. So of this perfect square, 2 divided by 2 is 1, so I'll have 1p and 1p. 16, the square root of 16 is 4, so 4 and 4. 1's plus, 1's minus. I can't go any further. So this is going to be my final answer. Okay? All right. Now, I actually have examples 5 and 6 continuing on the same slide. So we are going to work problems 5 and 6 all at one time. Okay, so it says factor each binomial. In this case, what we're going to be doing is the example problem we're going to do is pretty much covering your example 5, and then we're going to complete number 6, but only the practice problem. So 5 will be together, 6 will be on your own, and then of course you can come back and look at my answer on 6 and make sure that you've done it right. So on number 5, we have 9x to the third minus 25x. Okay, what do you notice about this? Do you see how they both have an x? All right, so this goes back to the beginning problem. Anytime everything in the problem has something in common, factor it out. So before we start doing anything here, we're going to factor out an x. So x is factored out. What's left behind? 9, I had 3, I took away 1, so I'm left with 2 x's. The minus sign stays. 25 is left behind. I had an x and I took it away, so that's it. All right, now let's reevaluate. So we have our x on the outside. Can we factor further? So hopefully you said yes, because notice that we have 9, that's a perfect square. X squared, even exponent, 25, perfect square. So when I continue this, anytime you factor out something, you got to keep it there. So I'm going to keep the x. I'm going to go ahead and draw my 2 binomials. 9, what's the square root of 9? 3, so I write 3 twice. X to the second. 2 divided by 2 is 1, so 1x, 1x. All right, for 25, what's the square root of 25? All right, 5. 5 times 5 is 25. 1 gets plus, 1 gets minus, and notice that x is a part of our final answer. Okay, I do have you doing practice problem, but not number 5. You're going to do practice problem number 6, okay? So try to do number 6 on your own. If you get stuck, go ahead and just watch me as I explain over the answer, okay? So I'm going to go ahead and work it, and then you can check your work with me. And we are on page 402 if you haven't started yet. Okay, so guys, on number 6, you did have to pre-factor before doing a perfect square. You can factor out 5 from both of these. So 80 divided by 5 is 16. 5 divided by 5 is 1. Of course, the y to the 4th is still there. So when I factor out 5, I have a perfect square minus perfect square. 1 is a perfect square because 1 times 1 makes 1. So I start with my first term. 16 square rooted is 4, so 4 and 4. Y to the 4th, so 4 divided by 2 gives me y squared and y squared. For the second term, the square root of 1 is 1. 1 times 1 is 1, so 1 and 1. 1's plus, 1's minus. Now, I didn't stop there because I noticed, although I can't do anything with this one, over here, I can take the square root of 4, I can take the square root of y squared, and I can take the square root of 1. So this one is actually going to go another step further. So the 5 stays, the 4y squared plus 1 stays. I break this one up into another set of 2 binomials. So square root of 4 is 2 and 2. 2 divided by 2 on the y is 1. So 1y, 1y. The square root of 1 is 1. 1's plus, 1's minus. Okay, if you choose to rearrange terms, keep in mind the sign of the term must remain with that term. So if you're like, oh, I don't really like the order of this, then you can rearrange it, but just make sure that you don't take away whatever sign is in front. So this is going to be example 7. We have negative 25m squared plus 121. Well, the rule is that if I want to take a perfect square and factor it, it has to be a perfect square minus a perfect square. Right now I have a negative perfect square plus a perfect square. But if I rearrange that, I can actually make it work. So what I'm going to do is I'm going to actually take the 121 and put it first. And I'm going to have that subtracting 25m squared. So by doing this, I didn't change the value. 121 is still positive and 25m squared is still negative. So now that I have a perfect square minus a perfect square, I can go ahead and write my answer. So I'm going to have 2 binomial sets. 121, if you need to put that in the calculator, you're welcome to. 121 square rooted is actually 11. So I'm going to put 11 and 11. And then 25m squared, square root of 25 is 5. So 5 and 5. And then m squared, 2 divided by 2 is 1. So 1m, 1's plus, 1's minus. Final answer. Okay, so you go ahead and try the practice problem on your own. We are on the very bottom of page 402. All right, so we had negative 9x squared plus 100. I rearranged it so I had it in the form of minus. So 100 was positive minus 9x squared. The square root of 100 is 10. The square root of 9 is 3. And the square root of x squared, 2 divided by 2 is 1. 1x, 1x. 1's plus, 1's minus. All right, When factoring sums or differences of cubes to the third power, notice the signs and patterns listed on page 403. So if you have your book, hopefully you do, since I've been asking you to do these practice problems, go ahead and take a look at page 403 in that lavender colored box. This shows the layout of how to write the answer of a perfect cube. And here's the difference between squares. Squares have to be a perfect square minus a perfect square. A perfect cube can actually be add or subtract. So a perfect cube plus a perfect cube, or a perfect cube minus a perfect cube. Each has a different set in its answer. So you need to actually pay attention to this little lavender box when you're doing practice problems or when you're doing your homework to see, okay, how's it gonna be written out? So before we do the practice problem, I'm gonna go ahead and just talk about how we know what the difference is. If you look at it, notice that everything between a perfect cube plus a perfect cube and a perfect cube minus a perfect cube is almost the same except the signs. The only thing that's different is the first two signs, okay? If you look at the last sign though, they're both plus. So no matter if you have a perfect cube plus or a perfect cube minus, the very end of writing out the answer is always gonna be plus. So let's work through this problem that we have right here together, and we'll refer back to this as we decide how to write that answer. Okay, so perfect cube. What do I mean by perfect cube? Well, there's actually a button on your calculator. You can do this. Instead of it being this, it has a 3 here. So perfect cube is the same number times itself 3 times. So on x to the third, whereas a perfect square is anything that's even, a perfect cube is anything that divides by 3, okay? So x to the third can divide by 3, so that means it's a perfect cube. 27. Now don't do just 27 divided by 3. It has to be the same number times itself to equal 27. So if I were to actually break up 27, I'm just going to do it over here. I know it's 3 times 9, and then 9 is 3 times 3. So if I break it into primes, it should be the same prime number times itself, okay? Well, it's not necessarily always going to be a prime, but it would be, you'd end up having 3 versions of the same number to be able to equal that total. So in this case, I know that 27 is a perfect cube because 3 times 3 times 3, the same number times itself 3 times. So let's take a look at page 403. Look at the rule that says if it's a perfect cube plus a perfect cube. So the very first thing is that we're going to have a binomial, okay? And we know that if we start with a plus, the first binomial is also going to be plus. Now, what does it mean by a plus b? Well, we have a to the third, in this case, x to the third, and 27. So the very first binomial, this sign is going to be the same. This number and this number, or this term and this term, comes from taking the cube root of the original term. So if I take the cube root of x to the third, I do that by dividing it by 3. So 3 divided by 3 is 1. So that's going to be an x. For 27, what's the cubic root of 27? 3. Okay? So you're taking the cube root of both of these for the first binomial. Then we're going to have a trinomial. This time we're going to have 3 different things that are adding or subtracting together. So if you look at the lavender box next to the one that says we're adding a to the third plus b to the third, we are actually going to take the square root of this. So what's the square root of x? X squared. Okay? Then it says as long as this was a plus sign, the first sign in my trinomial is minus. Then it says a times b. Well, what's a and what's b? In this case, it's from what I had in my first binomial. X times 3. We do want to make sure that the coefficient comes first. And then, as I said before, in that trinomial, the plus will always be there no matter what this sign is. So this is always going to be a plus. Then it says the last term is b squared. So in this case, b squared is 3 squared. Now don't write 3 squared. A number can actually be solved. So 3 times 3 is 9. And that's my answer. Okay? Now I want you to do the practice problem. Okay? So that's going to be on page 403. All right, so in this problem, it's the same type. It is a plus sign, so you're doing you're practicing the same thing we just did, just with new numbers. The cubic root of x to the third is x, 3 divided by 3. 64, if you can either do this in your calculator or if you just happen to know that 4 times 4 times 4 is 64, the cubic root of 64 is 4. So after that, the square of x is x squared. And here's a way to remember this if you're really just trying to have a way of memorizing this. Whatever this sign is, it's going to be the opposite here. So this sign is the same, this sign is the opposite. So I take my x squared, then it's a times b. So 4 times x is 4x. This is always plus, then you take the square of 4. 4 squared is 16. Okay, so z to the third, 3 can divide by 3, so that's a perfect cube. And 8, can the same number be multiplied 3 times to equal 8? Yes, 2 times 2 times 2. So that means that this can work for our rule. So I'm going to go ahead and set up my first binomial. So of my binomial, the sign is the same as the starting problem. So now I take the cube root of z to the third. 3 divided by 3 is 1z. 8, so you're taking the cube root of 8. You're not dividing it like we do variables. So the cube root of 8 we already said was 2. All right, now I'm going to start my trinomial. So the trinomial, we take this term squared. So z, if I square it, it becomes z to the second power. Whatever this sign is, and you can refer to the lavender box, whatever this sign is, this is the opposite. Okay? Then from there, we take the first term times the second term. So 2 times z is 2z. Then the last term is always plus, okay? And we take the second one in our binomial, in this case it's 2, and we square it. What's 2 squared? 2 times 2 is 4, and that's our answer. Okay, now it's your turn. Go ahead and do practice problem number 9. It's at the very bottom of page 403. All right, so on the practice problem, both of these are a perfect cube. So in the first one, the sign has to be the same. So cube root of x is x. Cube root of 125 is 5, because 5 times 5 times 5 equals 125. Then this one is this squared. So it becomes x squared. The sign is the opposite of the first one. Then this and this multiplied. So x times 5, I put the coefficient first, 5x. Then this is always plus, and then this squared, the second term squared. 5 squared, 5 times 5 is 25. All right, so our last one, we have 125, a to the third plus 1. Okay, so this is a perfect cube, this is a perfect cube. So we're going to start with our rule. Start with the binomial. 125 taking the cube root is 5. A to the third, the cube root of that is a. And then whatever this sign is, so plus. Cube root of 1, 1 times 1 times 1 is 1, so 1. Now I start my trinomial, this squared. So 5 squared is 25. A squared is a squared. Whatever this sign is, the first sign of the trinomial is the opposite. Then we take this times this. So 5a times 1 is still 5a. On the last term, it's always plus, and then 1 squared is 1. Okay? Let's see if this was meant to be a trick problem to go further. Nope, that's it. Okay, so this is going to be our final answer for example 10. All right, and then we do have one more example we're going to go through. Yeah, we're skipping the practice problems on both of these. All right, so this example is going to be our final one. Let me double check. Yes. This is going to be the final example for section 6.5. We have 54 x to the third minus 128 y to the third. All right. Okay, so going back to our original rule of if there's something you can factor out within the problem, go ahead and try to factor that out. So something that I notice here, 54 and 128, are they both divisible by a similar number? And the answer is yes. They are both divisible by 2. So we are going to factor out a 2. So 54 divided by 2 is 27. And then the x to the third stays, the minus sign stays. 128 divided by 2 is 64. And here's why this just helped us. By factoring out this 2, I now have a perfect cube minus a perfect cube. Before, 54 and 128 are not perfect cubes. So this actually helped us because now it's allowing us to see that we can continue factoring this problem. So this 2 is going to have to stay with our answer the entire time. So I know that because it's a perfect cube and a perfect cube, I'm going to start my answer with a binomial. So the cubic root of 27 is 3. For x to the third, 3 divided by 3 is 1x. And then for 64, the cubic root is 4. And y to the third, 3 divided by 3 is 1, so I'll have one single y. Whatever this sign is the same sign in my binomial. All right, starting my trinomial, I take the square of 3x. So 3 squared becomes 9, and then x squared, so obviously just x squared. Whatever this sign is, this is the opposite. Okay, so the second one is the 2 terms multiplied, so 4y times 3x, or you could also say 3x times 4y. Let's start with, in this case, the thing that really makes this problem different is that they both have a coefficient and they both have a variable in both terms. So we haven't had to do this before, but we're actually multiplying coefficients and variables together. So start with your coefficient, 3 times 4, that's 12. X times y. When you have different variables, put them in alphabetical order. So x, y. And then the last sign is always positive. And then we take the final term squared. So 4 squared is 16. Y squared, close the parenthesis, and that's your final answer. All right, so this concludes the video for 6.5. If you have any questions, please feel free to message me. You can either send me a remind message or you can contact me by email. And the homework assignment for 6.3 and 6.5 has been available on Canvas for a while now. Of course, I wasn't expecting you to do it until you were able to watch this video. So you can go there and get started on that assignment. I have made all chapter 6 assignments due the day of the test, which is set for the 24th of April. I'm considering giving an extension to possibly Monday. So just check Canvas to see on that. Just be aware that if you put it off to finish the chapter 5-6 test, that leaves you less time for the chapter 8 test, which has to be taken by May 5th. Now, I will say chapter 8 is really short, but it does involve all new material that you will have to learn. So don't push it off. I would say try to have everything done by the 24th as a goal, regardless of whether I change the due date. Homework is still going to be due the 24th, regardless of what happens to the chapter 5-6 test date. But also keep in mind that the chapter 5-6 test, all attempts have to be completed by the due date. So don't start the test on the due date. Otherwise, you're limited to just that day to take the test as many times as you need. So I've put a max on 3 attempts and your final score will be the average. If you're happy with the score you take on the first attempt, you don't have to retake it. It's just there if you want to try and improve your score. Okay? All right. Have a good day. Thanks for tuning in.